Hi, hello students. Welcome to BYJU'S exam prep and welcome to the most awaited session of BARC HAL 2023 operating system concepts. In this session, I'm going to give you the complete idea about the process concepts of the operating system. Stay tuned and focused because in the upcoming session for 1 hour or 1.5 hours, we are going to completely discuss about the operating system process concept from which you are going to face many questions. You may have many questions coming from your BARC exam. Let us start. Yep. Now, initially, when you talk about, just to suggest you, don't miss this session from Rakesh Talreja and Ashok Saxena, which you are going to, which is going to give you the complete strategy to what need to be followed for the GATE 2023 and 24, which is going to be streamed live on 5th March at 8 p.m. And stay tuned and follow this session very carefully so that you're going to get a complete idea what would be the scenario for strategy and the preparation and everything. You're going to get a complete picture of how you're going to prepare and crack the GATE exam in 2023 very easily, and all the fundamentals will get covered to the inside views. Now let us start without wasting any more time of process concept. This is Anil Sir. Let us start. What is a process? The fundamental question to be asked before we enter. Yeah, hi, A. Very good evening. Very good evening. Please share as much as possible so that this would be a very important session, and most of the people, they will be able to capitalize this session so that your friends will also be able to join, and your friends will also be able to crack the BARC exam so that they may secure a seat in the BARC. Yeah, let us start with the process concept. What is a process? To start with, a process, first of all understand something that the process is a program which is in the execution. As long as you don't execute any program, that will be sitting in the secondary memory. That is, let us say, for an example, for an instance, you have written a C program. In the C program, you have embedded 100 instructions altogether. All these 100 instructions, you have written, after which you saved this file and a .c extension, and you saved this. And as long as you don't execute, it will remain a dead entity. And where you're going to store, fundamentally secondary memory. As long as you don't execute, this is a passive entity which has no active meaning at all. But the moment you want to execute a program, you are going to bring this program into the main memory, right? So the program, once has been brought from secondary memory to the main memory, it becomes a process. Now, what is the significant difference between a program and a process? Let us see. This process concept has been called with several names. In a batch operating system, a process will be called as a job. In a time-shared operating system, a process will be called as a user program or a task. No matter whatever the name that is, everything, a program which is going to be executed, every program which is going to be executed concurrently is called a process. Process meaning a program which is getting executed concurrently. Names may be different from the type of the operating system to operating system. Now, as I told you, a program is an execution. Process execution must progress in the sequential fashion. That is, once after a process has been brought into the main memory, this process will be given a few more entities. Initially, every process will have something called a text section. Let it here. In the main memory, several entities will be created for a process. The initial portion is called the text section, and the next portion is called the data section, and the third portion is called the stack section, and the final portion is called heap section. Stay focused carefully. What is text section, what is data section, what is stack section, and what is heap section? When a program is not getting executed, a program simply consisting of only one section, that is text section. But the moment a program has been brought into the main memory, the operating system will allocate all these sections to a program. Then the program becomes a process. Now, what are these sections are about? The first section, which is called a text section, is going to hold all the instructions of a program. When a program has been brought into the main memory, all the instructions, which are in the form of functions, in terms of functions, will get directly transferred to text section of a program. What is data section? The data section of a program is going to contain all the global variables. For an instance, when you write a program, you're going to have a global variable declaration. There is a space in which you're going to declare the global variables initially. All the global variables that you declared, which has a span throughout your program, will get transferred to the data section of the main memory of that particular program. Next thing is the stack section. What a stack section is going to hold? The stack section is going to hold the local variables as well as the return addresses. Let us say when a function calls within a program, a function calls another function. A routine calls a subroutine. At that time, the current routine's return address will be saved into the stack. If you do have any doubts, you just can post it in the hi Anu, hi Durga Prasad. Please post your doubts here. Yeah. What is the heap section finally? This heap section is going to contain all the dynamic variables that are going to get created at the runtime of a program. When you execute a program, during the execution, you may create some dynamic variables by using some methods such as calloc or malloc, right? You have calloc and you have malloc, which are going to create the dynamic variables during the runtime of any program. If you create some dynamic variables during the runtime, those will directly get transferred to the heap section of a program. When a program has all these entities in the main memory, then this program is called a process. The moment one program is coming into the main memory, operating system will allot all these entities, all these, the spaces in the main memory, text section, data section, stack section, heap section. During the creation of all these entities, a program is said to be in a state which is called new state. You know that a process will have several states which we are going to understand in the next few slides. But when a program is incoming, let us when a program is getting transferred to the main memory, operating system. Let us say I'm an operating system. A program is incoming. I need to allot all these entities to the incoming program, during which this program is said to be in the new state. Okay. Next, any doubts so far? This is how it exactly looks like. We do have a text section, data section, heap section, and a stack section, and then the program space. Now, let us understand carefully here. Not to forget, a program may also access kernel section of the main memory. What is the kernel section? The kernel section of the main memory is going to contain the routines that are not transparent to the programmer. For an example, a program has to call a system call. For an example, this program is about to, let us say this process is about to execute one instruction called printf. What is printf? Printf is a system call. When you execute printf, corresponding system call within the kernel is going to get executed, which is the operating system's exclusive routine. So every time when a program is going to execute, is going to call an instruction which is going to trigger a system call within the operating system, immediately the corresponding system call within the kernel will get executed. So the program may also use the kernel section, which is not transparent to the program. The moment the printf is executed, there will be a mode switch from the user mode to the kernel mode. The mode will get switched, after which the operating system will execute the system call, the corresponding system call is for printf on behalf of this program, so that you will be able to see the desired outputs on the screen. But mind you, this printf is not a user instruction. This is a system's instructions. As of now, you understand that the printf is a system instruction which is going to execute a system call, which is also called a protected instruction. Sir, what is a protected instruction? Write it down somewhere. A protected instruction is an instruction which is going to access the kernel section of the main memory. And the kernel section is not available directly to the user. If you have to use the kernel section, the mode will have to be switched from user mode to the kernel mode. Any doubt so far? Of course, When you get into the details, of course, the printf will have two functions, but mind you, these are not functions, mind you. These are the system calls that are going to get triggered. One instruction, one protected instruction may call several system calls within. But when you talk about a system call, you must understand that the system call is an integral part of the kernel section. I hope you got the point. Any doubts so far? Yeah. Now, next thing that we need to understand is what is the state of a process. As I told you, the process can change its states during the execution. The moment a program gets into the main memory, as long as it is incoming, the operating system is going to allot or allocate, whatever you call, all the sections, all the necessary sections, such as stack section, heap section, data section, and text section. The program or a process is said to be in the new state. Okay, the process is being created. The necessary sections are being created by the operating system for the incoming program. The moment the program is completely available within the main memory, then that becomes a process. The moment it becomes a process, then it is said to be in the ready state. The moment a program comes into the main memory, then it is said to be in the ready state. What is ready state, sir? Ready state states that a process is ready for execution. That process part is done. The process has come into the main memory, which is the actual rule for execution. If you want to execute a program, what is the fundamental rule? The program must be made available within the main memory, right? That program's part is done. It has to come and sit in the main memory. It is done. The next thing is, it is ready to execute. When a program is completely available in the main memory, then this is called ready for execution, right? So, the moment when program becomes runnable, the moment when a program becomes ready for execution, sooner or later, operating system may select this program and send into the CPU for the execution. The moment a program gets into the CPU for the execution, then it is said to be in the running state. That is, as long as a program is executing, a program or a process. I may use this program or process interchangeably, but technical term, the correct term to use in terms of the operating system, from the perspective of the operating system, it is process. When a process is getting executed within the CPU, then it is said to be in the running state. Okay, so hold on. Running state, when a program goes to processor, within the processor, the program is executing. Sooner or later, this program may go to perform an IO operation. Here, one wonderful example is, take the same example of the C program. Within your C program, after a few instructions, you have written a printf statement. Okay. During the printf, what is going to happen? The moment printf instruction gets executed, then the thing what you want to print, the string what you want to print will have to be printed on the screen. And mind you, there is the IO device where it is going to be printed. That the thing that is going to be printed is on the screen, right? The screen is an IO device. IO device cannot respond as faster as the CPU. CPU is the fastest device. Comparatively, relatively, IO devices are very slow to respond. Okay, so the moment one IO instruction is executed, a program may go to perform an IO operation. The moment your screen responds, then the string what you want to print will be printed on the screen. But during which it will take some significant time. During this time, a process is said to be in the waiting state. Whatever it is, either it could be called as either a program or a process, but this is said to be in the waiting state as long as it is awaiting for an IO device to respond and do the necessary job for you, such as printing a string on the screen. Okay. Finally, a program may get terminated. A process may get terminated. When a process gets terminated, let us say a process gets completely executed, it will get terminated. Sometimes a process may get also terminated abnormally. Any doubts so far? We will talk about this wait and ready state. See, suspended wait and suspended wait and suspended what do you call ready state. in synchronization. Here, our total class is just confined to the concept of the process and scheduling. We are talking something about a synchronization which we are going to cover in tomorrow's class. For answer rhetoric questions, a process may also wait for a semaphore, but that we are not covering right now. Here, waiting state means that a process is awaiting for an IO device to respond. We will limit the discussion till then. Tomorrow we are going to completely get into the details of these semaphores and critical section, why a process has to wait, why a process has to get blocked, and when it gets revoked. I'm going to give you an insight view of that tomorrow. Meanwhile, hold your horses for a while. Just limit the discussion to the process concept, how the process gets created, how the process will get terminated, and meanwhile, what is the transformation of the process from one state to another state. Not just this. I'm going to give you one live example by taking the Linux operating system. So stay focused and stay tuned. Yeah. What is terminated? Terminated meaning a process gets executed. The operating system should terminate the process. Sometimes a process may also get abnormally terminated. For an example, it executes an illegal instruction which cannot be executed by the CPU. Let us say you try to write an instruction which a divided by 0. A divided by 0 cannot be executed at all. At that time, the process which contains this illegal instruction will have to be abnormally terminated. So, every process right after its execution, it should be terminated, or else if it executes some illegal instructions, the operating system will terminate this process. So, a process will transform one state to another state. These are the states that are going to be attributed to a process as long as it is executing. Yeah, let us understand this process state diagram. Stay focused, all of you. Stay. Hi Akshita. Hi Bhumi. Hi Ritik. Now, let us understand this. You know that there is a process P1. Okay, P1 is in the new state. What do you mean by the new state? The P1 is being given text section, data section, stack section, and heap section, during which P1 is said to be in the new state. The moment all the sections are created, the moment all the entities are attributed to P1, then it goes to the ready state, right? P1 is right now in the ready state. When P1 is in the ready state, it means that every entity of P1 has been created in the main memory, and the only part left from the operating system is to allot the CPU time for this P1. Okay, now as long as it is in the ready state, let us say the moment the P1 is in the ready state, sooner or later, operating system will select this P1 and send this into the running state. What is running state? Running state meaning the process is executing in the CPU. Hold on, here I would like to introduce one more state which is called interrupt. I can't say it's a state, but it's an event. What is an event? Let us say now my P1 is a running state. Okay, stay focused because you may get a question surely in the BARC exam or HAL exam on this process state diagram. If you actually can understand this, you're going to answer at least one question from this. Now, a process P1 is executing. Now the process P1, generally it has two legitimate options. It may go to IO waiting. For an instance, it may want to perform an IO operation. When IO operation is about to be performed, this P1 will go to the IO device, respective IO device. So the P1 is said to be in the waiting state. From the running state, a process may also get terminated. Right? Let us say all the instructions of P1 gets executed. So P1, in case of an IO operation, may go to the waiting state. Same P1, in case of all the instruction gets executed, may get terminated. These are the two legitimate states for P1. But hold on. But unfortunately, P1 can be also sent from running state to the ready state. Let us say there comes P2. This P2 has higher priority than P1. Let us say you're in the queue. You're in the temple queue. Completely you're about to enter into the sanctum. But there comes a VIP. VIP is our P2. The moment P2 comes, if P2 has greater priority, higher priority than P1, The currently running process, which is P1, which is also said to be in the running state, will be printed back and put in the main memory. So P1 got nothing to do rather than waiting for P2 to finish. Now, okay, you might have already heard about this preemption and higher prioritized process and lower prioritized process, but I'm going to give you some important details which are higher prioritized processes. Stay focused. When a user requests, as long as you switch on the computer system, many processes gets executed, right? Although you don't touch anything even, some internal process gets executed which are actually required to stabilize the operating system. Okay, some processes are already running. Now let us say you made a key depression, you used keyboard, you moved mouse. That means that a user process is ready for execution. When you press a key, you request the operating system, you request the CPU to reciprocate to your request. Immediately the CPU, without having no delay, it needs to take your request, it needs to process your request, it needs to execute your program. All the users' programs must be dealt with the highest priority. Let us say this P1 is not a user program. This P1 is some other program than the user. Now, there comes a request from, a user. Generally, how user is going to make a request to the operating system? By using the peripheral devices. So, all the programs that belongs to the peripheral devices has the utmost priority than any other program which is running. Even within the peripheral devices, we have higher priorities, lower priorities. But if you don't consider that part right now, if you communicate with the computer system with any of the peripheral device, immediately the computer system, either you call it operating system or a CPU, should suspend all the other processes and should reciprocate to your request, which actually being generated by one of the IO devices. I hope you got it. Okay. Any doubts so far? Bhumi Prajapati, suspend wait state, please. I told you already. In the synchronization part, I'm going to cover this suspend wait state. What is the suspend? When a process will get suspended and when a process is going to get blocked. That is tomorrow's session. Today's session, we're going to limit ourselves to the creation and deletion of the processes. Okay, process creation, process deletion, and yes. Okay, that's it. So any doubts so far? Any doubts so far? So here an important point to note is users processes. Has higher priority. That means, of course, first point lead to the second point. How user is going to trigger a request? IO devices. All the IO devices, all the processes that are coming from the IO devices will have the highest priority whatsoever. So when IO device is making a request to the operating system without having no doubt at all, without having any ambiguity, operating system should suspend the current process, should take the request of the IO device. During an IO device request, an IO routine will get executed. Okay, IO routine gets executed. This IO routine will also be called as the service routine. Okay, these are all the things that you need to understand carefully. Yeah, any doubts so far? Fine. Bhumi, Ritik, and yeah. Next thing is, what is a process control block? Stay focused here. Here, you might have heard about a process control block. Let us understand something. I'm going to give you the complete core view of the process control block. How a process control block is going to be designed. As I told you, when a program becomes runnable, that will come and sit in the main memory. The moment a program comes into the main memory, immediately, in addition to allotting all the necessary sections of the program, such as text section, data section, stack section, and heap section, the operating system will also create something called a process control block. What is process control block? How a process control block is going to be created? let us understand, let us talk about the design part of the process control block. For designing this process control block, the operating system is going to use several data structures. Process control block for any process is a collection of data structures. Okay. Why the data is needed to be structured? Can I have a question? Bhumi? Why we require a data structure? Why do we need a data structure, first of all? I'm awaiting the answer. Fine. Stay focused. I'm going to give you an important detail behind the creation and behind the design of any data structure. Okay. This is as follows. Go and observe your memory chip. Okay. This is a pure memory chip. Here we are not rendering operating system. Here we are not having any programs within the main memory. Simply, it's a raw memory chip. Okay. If it is a raw memory chip, if you just can have a look at, this is physically divided into two parts. Any memory chip, take any memory chip. It could be connected to your i3 processor, i5 processor, i9 processor, or any Snapdragon or Atom processor. Any memory chip has been divided into two physical parts. One is instruction part, and one more is data part. Okay. One is instruction section and one more is data section. Instruction section is contiguous. What is contiguity? Because all of you, what is the definition of a program? The definition of program is nothing but it's a collection of instructions. It's a set of instructions. That is, if you execute a first instruction, there has to be a second instruction. There has to be third instruction. There is a sequence. There is a flow. We need to follow the flow. That is the very reason why the instruction memory of your total memory chip must be contiguous. That is, the instruction must be aligned one after another. The second instruction must be aligned right after the first instruction, not somewhere else. Otherwise, there won't be any flow of the program. Your program cannot be executed. That is the very reason why instruction memory is contiguous. Got it clear? But data memory, I can't give you the guarantee. Data memory is, I will say, NC, non-contiguous. What is non-contiguity? Non-contiguity meaning the data, of course, let us say the data memory is from 500 to 1000. Okay. You can ask me, sir, after 500, there will be 501 location. No? Yes, of course, right after 500 location, there is a 501 location. But they don't take the contiguous elements. Instructions. Let us say first instruction has an operand at 500 location. First instruction operand, where it is available? In the 500 location, it is available. Now, where is the second instruction operand? Mind you, second instruction operand, I can't give you a guarantee that it will be available at 501st location. Second instruction operand may be available in 799. Third instruction operand may be available in 650. All the operands of any program are scattered across the data memory of the specific program. I hope you got the point. Why do we require a data structure already? In order to maintain a relationship among all the elements, all the disjointed elements, we require a data structure because they do belong to a single program and they are required to be connected somehow or the other. What are the different data structures? Array. It will create a relationship straight away, like the instruction section. Array is the contiguous allocation of the locations, right? Sorry, contiguous allocation of the locations. Yes, I am. Main memory locations in the data memory will be collected together and will be given for your array. Of course, it's a fundamental data structure. But the problem with the array is we may not get those many contiguous locations which is equal to the size of array. Okay, array size has been 100, fine. Array size has been 200, fine. Array size has been 1000. Array, I can't find out those many empty contiguous locations. This is the very reason why we go to list, we go to linked list, we go to double linked list, we go to circle linked list, we go to hash maps, we go to bitmaps. We have several data structures, but in order to maintain a relationship among the elements which are collected together, which are disjointed in the data memory, we do require a data structure. Whatever the data structure you want to use. Okay. Yeah. Any doubts? Fine. Yeah. This process control block will use several data structures. It will collect together. It may not look like this. Okay, let us understand and let us perceive the things correctly. Have a good perspective. Process state cannot be connected to process number, okay? Process state will be in some data structure, process number in some other data structure. I may use a linked list to connect and establish a complete, what do you call, the process control block. Did you understand? The process control block may also be disjointed entities, but I will use some of the other data structures to establish a link. Okay, so the moment a process becomes runnable, immediately the operating system will allocate. The operating system is going to create a process control block which has a process state, a process number, an ID, unique ID. I can't say the number. Every process will be identified by its unique ID. The process, this will have a program counter value. What is the program counter? If the current instruction is 21, next instruction is equal to 22. Okay, the program counter value will be specified here. And next one is, what is registers values? When a process is executing in the CPU, it may have several registers value, R1, R2, R3, program counter, accumulator. All the register values belongs to that process. All the registers value will also be specified here. Okay, and this will come into the picture when the process gets suspended. I will talk about that tomorrow. Memory limits. Okay, what is the base? What is the base of the process? What is the end of the process? Okay, the process is available from 250th to 350th location. The process is strictly allowed to access through 250 to 350. The process cannot try to access any other location which is not allocated to it. Okay, and the list of the open files. What are the list of the open files? When a process is being executed, it may access several files. All the files which are being opened by this process concurrently will be specified in the PCB, because when a file has been opened by one process, as long as this process is using that file, it should not be opened by any other process. So operating system keeps the track of the files that are opened by every process. So I do have a process state, a program counter, CPU register, CPU scheduling information. Of course, in a scheduling queue, what is the position of this process and what are the scheduling algorithms that are being followed here? What is the memory management information? I told you there will be a base register. In the base register, the starting address of the process will be stored. There is a limit register. In the limit register, the ending address of this process will be saved. What is the accounting information? Let us say this process has been given instantly 200 milliseconds. The moment the CPU burst started, it will be counted from this 200. It cannot exceed this 200 milliseconds. So, in which what is the total CPU used and the clock time elapsed since start, 200 milliseconds will be, there will be a counter that is allocated to every process and the time limit. These will be done. These will be represented in the accounting information of a process. IO stated information, as I told you, the list of open files, the IO devices that are being used by the process will be specified within the process control block. No, I told you already. PCB is a collection of data structures. You got my point. Not a single data structure. Tell me how we are going to maintain everything in array. Is it possible? No. PCB has to be viewed as a collection of data structure. Let me tell you, okay, I'll give you a clear idea here. You're going to design an operating system. The data structures which you feel to be implemented, rather, to implement PCB, you can use. For me, I use stack. I use, circular linked list. I don't want hash maps. So this PCB can be designed by using any of the data structures. Every entity I can design by using one data structure. So it's not a single data structure, try to understand. And the PCB design is different from OS to OS. I'm an OS kernel developer. I like only 3 or 4 data structures. I will implement my PCB by using only those structures. The data structure because there are several factors acting on this. Did I make it myself clear? Okay, it's a collection of data structures. I hope you got my point. Yeah. Next, the process scheduling. Of course, what is this process scheduling? Why do we need to have a process scheduling first of all? Simple thing is, we don't need to go through Ramayana or Bhagavad Gita to understand this. It is very simple. Okay, this is, let us say, there is secondary memory, and I do have main memory also. Okay, so there is secondary memory and there is main memory. Why do I require? Forget about main memory for a while. Talk about the secondary memory. Why do I have? Why do I need to have a secondary memory? Secondary memory I do require because the total number of programs I do have is more than that of the size of the main memory. I can't accommodate all my programs into the main memory. Total size of my programs is equal to 1 TB. Can you transfer every of your programs into the main memory? No. My main memory size is very limited, 4 GB. Okay, initially you may have several files, several movies, several games, and you do have a total of 1 TB files. Okay, but for operating system, everything is a program, right? So initially all the programs will get dumped into the secondary memory. Okay, the moment you switch on the computer system, operating system needs to decide which are the programs to be executed right now. For that, operating system will make a decision among the programs that are available in secondary memory and send a few programs into the main memory. Okay, so this is a decision making. I will say DM, which is a decision making. Okay, this is also called scheduling. Operating system should follow several ways to identify which are the programs that are needed to be transferred into the main memory. Okay, it may take several calls. After finally, some programs will get transferred into the main memory. So it is one decision making. Decision making number one. Right from main memory now. Main memory is a collection of programs. Let us say I do have 100 programs which have been chosen and transferred from secondary memory to the main memory. Now main memory has 100 programs. Now operating system has one more overhead to select what is the next program to be sent into the CPU. So for that, decision making 2 must be done. Okay, so this decision making must be very effective indeed, in such a way to increase the throughput, madam. Sir, whatever you're listening to my class, stay focused. This term throughput, as long as you work as a software engineer, as long as you work as a system designer, as long as you work as some developer who is related to the computer system, will never leave you at all. All the designers, no matter what kind of a designer you are, you could be a software developer. In the software developer, you might be a kernel developer, application program developer, or else you are a CPU designer. In the CPU designer, you're just a control unit designer, or a ALU designer, or a pipelining designer. No matter whoever you really are, if you are a designer or a developer pertaining to a system, your fundamental goal, fundamental objective is always to increase the throughput. What is the throughput? Throughput is increasing the number of tasks that are being executed. I'll give you one more information regarding this throughput. Stay focused. Throughput is, again, it's not a rocket science. There might be several calculations to to understand the throughput. Stay focused, understand carefully. What is the job of the CPU? The job of the CPU is to execute one instruction at a time. That's it. Other than that, CPU doesn't know anything. CPU doesn't know about a software. CPU doesn't know about a program. CPU doesn't know nothing about anything else than the current instruction that is being executed in it. CPU, 1 gigahertz CPU. We'll let it here. 1 gigahertz CPU. 2 power 9 instruction it is capable of executing. So, but 2 power 9 cannot be reached. There are several factors restricting us to execute all these, the capability, to reach this capability, maximum capability of the productivity of the CPU. So initially, let us say we'll start being a designer. If we can achieve 2 power, what do you call, 1 nanosecond, right? I will erase this. Just a minute. Is it visible? Is it visible? Is it visible? Hi, BYJU'S. Yes. It is 10 power 9. Fine. So the CPU is the fastest device, but we have to tap the best out of the CPU. But there are several factors restricting us to reach the maximum potentiality of the CPU. So initially we will start with, let us say my CPU is capable of executing many instructions for 1 second, 10 power 9, let us say. But I can't reach 10 power 9. If I initially reach 10 power 2, fine. 10 power 3, fine. 10 power 4, fine. So throughput is, the continuous striving for all the designers. So the throughput is the fundamental objective for any designer. I hope you got my point. Yeah. See, the decision making one is called job scheduling. What is the job scheduling? Selecting the jobs from the secondary memory and sending them into the main memory. Okay, this is called job scheduling. Decision making 2, selecting one process out of the main memory, sending in the CPU is called CPU scheduling. Okay, and there are other terms also associated to this. The job scheduling is called long-term scheduling. The CPU scheduling is called short-term scheduling. We'll talk about this in our next session. Maintain scheduling queues of the processes. Job queue, set up all the processes in the system which is in the secondary memory. Okay, ready queue, set up all the processes that are available in the main memory which are waiting to execute. What is the device queue? Not only job queue and ready queue, there are several other queues that are in the system. One of the important queues is the device queue. In the next slide, you're going to understand. See, how to maintain a queue. The moment a process comes into the main memory, operating system will have to maintain a ready queue. Okay, this ready queue is simply not orally telling. Operating system will create a queue for this by using a linked list data structure. Initially, the queue will have a header and a tail. The header will point to the first PCB which is ready for execution. Tail is going to point to the final PCB which is finally available in the list. And each and every PCB has a pointer which points to the subsequent PCB in this queue. What is the ready queue? Ready queue is a queue from which operating system will collect the processes and send them into the CPU. First of all, the eligibility for a process to be selected by the operating system to be sent into the CPU is to be put into the ready queue. The process must be put into the ready queue. I hope you got my point. Any doubts so far? Job and a process. There is no job, Bhumi. Sorry, there is no difference, Bhumi. A process means a program. See, listen. I will tell you the distinct difference. When you talk about a program, if you say program, if you say process, you may interchangeably use. But everything, when it comes to the operating system, either you may call it as a program or a process or a job or anything. It is simply treated as a process only. The program which is in the execution, program is a dead entity. Program is not at all considerable entity for an operating system. The operating system will treat a program as a program only when it is brought into the main memory. So, technically speaking, the process is a program in the execution. Some operating systems call these processes as jobs. Some operating system call this process as processes itself. Most accepted term is process. Process is a program which is simply in the execution. I hope you got my point. Okay. Yeah. So, did you understand this ready queue? Let us say this is a ready queue. Right after which one program has been selected. This PCB 7, that is 7th program has been selected and sent to the CPU. Now 7th program is executing within the CPU, after which this 7th program wants to perform an IO operation such as printf. The moment it performs the printf instruction, then this process will be sent to the corresponding device. Let us say this is the device. Let us say there is printer. Printer is not here. Anyhow, let us say this process wants to perform a writing on the magnetic tape, and it will be appended to the queue which is awaiting at the magnetic tape. System also has the device queues, as you can clearly see on the screen. Ready queue is the queue of the process which are awaiting to execute in the CPU. Device queue are the processes that are waiting for each device. Let us say one process wants to perform a magnetic tape writing. After executing such instruction in the CPU, that specific process will be appended back to and appended as a tail within that specific queue. The process may switch in between one queue to another queue depending on its requirement. So from ready queue to the device queue, after which it may go to ready queue, it may also go to the device queue. During the life cycle of a process, it will switch in between ready queue and the device queues. Finally, One final time when it gets executed in the CPU, the process will be completely terminated. Did I make it myself clear? And any doubts so far? Next, let us understand about schedulers. Long-term scheduler and short-term scheduler. We discussed, right? We discussed about long-term scheduler as well as short-term scheduler. What is the long-term scheduler? What is the short-term scheduler? Stay focused and understand. I will write it here itself. Let us say I do have secondary memory. I do have main memory. These are programs. Okay. So let us say several programs are here. Main memory also has programs. Technically speaking, these are processes. CPU. Why do we call it as a long-term scheduler and a short-term scheduler? When the operating system is going to make a decision, which are the programs to be sent to the main memory? This is secondary memory, mind you, and this is main memory. Which are the programs to be sent to the main memory? Then it's called one process called job scheduler. Understand, this is also a process. This process will be sent into the CPU that will be executed for a while, in which it is going to evaluate an algorithm, after which finally some processes will be selected from secondary memory to the main memory. Did I make it myself clear? In order to select a few processes, operating system will execute one program. That program must get executed within the CPU, after which the output of the program will state which are the processes needed to be sent from secondary memory to the main memory. So after executing this job scheduler, a few processes will be sent from secondary memory to the main memory. Now main memory holds some programs, and now operating system should execute one more program which is called CPU scheduler. When the CPU scheduler gets executed, it is going to evaluate a different algorithm. The output of that algorithm will find out which is the next process to be sent into the CPU. Did you understand? Now, more importantly, these two also are the programs. Got me? There is a very reason why we'll call it as long-term scheduler, short-term scheduler. What is the long-term scheduler? When long-term scheduler gets executed, after, it doesn't execute so frequently. How frequently the operating system, long-term scheduler gets executed. Once the long-term scheduler gets executed, a few programs get transferred to the main memory. After that, operating system don't need to execute the long-term scheduler as long as all the programs not executed here. Long-term scheduler will only be executed right after all these programs left the main memory. But scenario will not be the same for the short-term scheduler. Short-term scheduler typically executes in between every process. When one process gets executed, immediately short-term scheduler goes into the CPU. That program gets executed in order to find out what is the next process to be sent into the CPU. This is the very reason why job scheduler is called long-term scheduler. CPU scheduler is called short-term scheduler. Understand carefully. One of the major headaches, one of the major burdens of the operating system is the schedulers. Scheduler is also a program. When the scheduler executes, significant CPU time will be wasted. Scheduler program, when it gets executed, it doesn't add anything to your throughput because it is not user program. Scheduler program is only there because to select the processes. So no productivity will happen to the CPU. No productivity will happen to the operating system. So this is an overhead to the operating system. In that case, long-term scheduler is somewhat, better because it doesn't get executed frequently. Short-term scheduler will get executed very frequently. So the short-term scheduler, let us say it is a culprit. In between every process, it will go and execute and kill the CPU time. How much? Let us say a short-term scheduler execute for 10 seconds, after which it selects a process which needed to get executed for 100 milliseconds. This 10 seconds is the time waste. In 110, what is the actual CPU time is getting wasted? 0.9% of the CPU time is actually getting wasted. So we can't do anything. If you don't, you have these schedulers, CPU time will get wasted. The productivity will get reduced. The throughput will get reduced. I hope you got my point. Okay. Now, and when it comes to the long-term scheduler, there is an additional job attributed to that. The additional job which is given to the long-term scheduler is, the long-term scheduler will need to find out the proper mix of the programs. Some programs are called CPU-bound programs. Some programs are called IO-bound programs. Sir, what is a CPU-bound program? What is the IO-bound program? You know that when the process gets executed within the CPU, it may go to the IO device and comes back to the CPU. The programs which spend more in the CPU, less time in the IO devices are called CPU-bound programs. The programs which spend more in the IO devices, less in the CPU are called IO-bound programs. Operating system needs to find out a proper mix of these programs in order to make sure that none of the CPU time, neither of the CPU time nor the IO device time is actually wasted. Okay, so it has to find out a good process mix. After which, if it can send into the main memory, so if we can have a composure of these programs, neither of the CPU nor of the IO device time actually gets wasted. Okay, so we do have a long-term scheduler, we do have a short-term scheduler, and the long-term scheduler is attributed, is overloaded with one more responsibility, that is to identify the good process mix to be sent into the main memory. Okay, in addition to which, I also do have something called medium-term scheduler. What is the medium-term scheduler? Let us say more programs are sent into the main memory. When more programs are sent into the main memory, more than a threshold point, the system's performance will be drastically reduced. There is a threshold. The operating system also is not a god, cannot do miracles. There is a rate at which the operating system can service the programs. But at some point, the operating system will be hands up. I can't execute all these programs. At that time, the CPU's performance will drastically memory, so that main memory can have only sufficient number of the programs that are needed to be executed, that can be executed by the operating system. Any doubts so far? Sir, for process in a device queue, it must first pass through the ready queue. Yeah, no process can directly go to the device queue. First of all, every process must be sent into the CPU, after which then only it goes to the device queue. Okay. Sir, a short-term scheduler is responsible for preemption. Scheduler doesn't preempt. Scheduler doesn't preempt. Interrupt will preempt. Preemption will happen during the interrupts. Interrupt is a hardware signal. Okay, during the interrupt, operating system itself, it is going to make this preemption. I hope you got my point. Yes or no? Scheduler, what is the scheduler? Scheduler is an algorithm. What is the last point? Interrupt, see, fine. What is an interrupt? One process is inside, P1 is inside, P2 is coming, P2 admits the operating system, I have more priority. Okay, then operating system uses the interrupt signal. Okay, of course, interrupt will be generated. When CPU is interrupted, that means that there is a higher prioritized process. Immediately context switch will happen. The process will come out to the main memory, the incoming process will go in. Okay, this is what? Context switch. This preemption will happen by using two modules. One is context switch, one more is dispatch. Context switch is exchanging the process. Dispatcher is a module which is going to give the control of the CPU to the incoming program. So this process switch will happen by using these two things. One is context switch, first one is interrupt, second one is the context switch, third one is a dispatcher. All these three things are responsible for process switch, getting one process out and sending one more process in. I hope you got my point. Can we go to the next slide? Medium-term scheduler, I also told you about this. Next, let us get into some important details and some important topics of this process management. Now, let me tell you fundamentally. Dispatcher is a module which is going to give the control of the CPU to the incoming process. It doesn't send. Sending will be done by the operating system. Dispatcher will give the control of the CPU to the incoming process. Okay. Yeah. Hi, Saubhagya Naik. Now, let us enter into some important things. Here, the operating system as its main job is to deal with the processes. What are the prerequisites to manage these processes? What will be covered in this process management of an operating system? As you can clearly see, first of all, operating system should be able to create a process and delete a process. For that, I will use the best example Linux shortly. So during a higher prioritized process arrival, the operating system should also suspending the suspension of the current process and resumption of the same process. So operating system should provide a efficient mechanism for suspending a process and also resuming a process. Okay, and sometimes understand carefully. Sometimes the operating system should make a communication established in between processes. Mind you, stay with me, all of you. Are you with me? Let us draw a main memory diagram. This is our main memory. P1 entered into the main memory. Operating system gives the spaces, what are all required. P2 entered, P3 entered. Okay. Now, the best practice of the operating system is to keep all these programs independent. As long as these programs, stay independent, remain independent, there won't be any troubles to the operating systems whatsoever. What is an independent program? The program which is going to be allotted with a few resources will never share these resources to any other program. So the operating system will allot the resources exclusively to all these programs. Let us say P1. When a P1 comes in, it requires the resources. What are the resources? Resources are CPU time, main memory, and IO devices and files. Okay, some CPU time has been given to P1, some main memory space has been given to P1, IO devices are given, files are given. All these resources are exclusive to only one program. Similarly, every program when comes into the main memory, it will be allotted with its sufficient number of resources. Operating system makes the resource exclusive only to the specific process. But all these programs becomes independent. Okay, but sometimes some programs want to communicate with each other. Let us say P3 wants to communicate with P1. At that time, this P3 will request operating system, Mr. Operating System, I want to communicate with P1. Then operating system holds its head, because it is the very area, this is the very point where the operating system is going to see itself into some serious troubles. I will tell you, the heartbreaking, points for the operating system are 3 terms. In the entire dictionary, operating system doesn't like 3 statements. One is, cooperation. Cooperation meaning what? Communication can also be called as a communication. Next thing is concurrency. Cooperation, concurrency, and preemption. When these things happens together, then operating system will get a heart attack. Why? Because this is the point where the operating system should get into the lot of trouble, should face a lot of troubles. Okay, so the process communication triggers all the possible troubles to the operating system. So operating system nevertheless, operating system should establish a communication in between those processes which want to communicate with each other, without which those processes cannot execute at all. Okay, so operating system should provide effective mechanism for process communication. As the process communication may lead to several problems, it also needs some effective synchronization mechanism, so that all the troubles that are being faced by the operating system are resolved in a manner in which the processes will execute in a hassle-free environment. Okay, so in addition to which, the operating system should also provide a mechanism for process scheduling, which is not given here. And the operating system should also provide an efficient mechanism for deadlock handling. About this deadlock, we are going to understand in the next sessions. Any doubts so far? Any doubts so far? Screen right now, I missed the point, I guess. Okay, sorry. Providing the mechanism for deadlock handling. I guess it is completely visible right now. Okay, now it is completely visible. Yeah, process creation, process termination, and so on as the detail next. Stay focused, all of you. From here, we're going to see the process creation in the live environment. For this, I'm going to use Linux operating system. Sir, why you are using Linux operating system? Why not Windows? Windows is not transparent. Linux is the best operating system so that we can have a transparency. Linux can also be customized, but Windows is not a transparent operating system. Windows will release only the modules of the code for the case studies. But Linux, every total operating system, every instruction, every module of the operating system is available for case study. It is completely transparent. So I will use Linux. Let us understand. Stay focused, all of you. Within no time, we can finish this and we will be able to solve any question on this process creation. So the moment computer system is started, initially the operating system loads its kernel portion. Got me? This kernel portion will be loaded by a process which is called bootstrapper. The bootstrapper gets executed, typically which is in the ROM. After which kernel portion will get loaded. Right after which system programs will get loaded. Right after which your application programs gets loaded. Right after which the user space will get created. Let us say this is the user space. Okay. This kernel is basically collection of services. Okay. All the services of the operating systems are made available within the kernel. But some services are also available outside the kernel, which are called daemon services. Okay, but these services can also be active as long as the system is switched on. Now that is not our part. Right now what we are talking about is a process creation. Every operating system right after all these entities have been created within the main memory is going to create a root process. Root process in a Linux is init. Okay, this init is going to create in tandem several other processes which are required to start the system, to initialize the system. Okay, then it will create a tree of processes. But a root process of all these processes is the init process, which is called to be as a grandparent process within a Linux operating system. Transparent Linux meaning what? See, Linux code is completely available. When it comes to the Windows, you can't see the code of Windows, how the Windows operating system is created. You got my point? You got my point? For Linux, each and every instruction that is designed to create Linux is completely visible for the user. You can create, let us say Saubhagya, right? You can create your own version of the Linux operating system Saubhagya. You can you can customize the Linux operating system in that way. Okay? It is a transparent. I hope you got my point. Right, Bhumi? Right, Anu? Yeah, now, how the process is going to get created? Now, in order to create a process, we require a parent process. A parent process will create a child process, and a child process will create some other process. Then a tree of process will get created. But in order to create a child process, I do require a parent process. Now, let us understand. Upon a process creation, what is actually required? Now, let us say there is a process A. Process A is creating process B. Got me? Process A, which is a process, is creating process B. Okay. Now B is a child process to A. The moment B is being created, as it's a child, B requires something. The first one which is required by the child process is the resources. Okay. It can be viewed as the real world. When we are about to give the birth to children, the children that are going to be created by ourselves require the resources, right? Of course, looking at the resources only we give the birth. Okay. So now, similarly in the operating system also, every time when a new child has been created by a parent, this parent is responsible for allotting the resources to the children. Again, what are the resources? CPU time and a main memory space, files, and any IO devices which are considered to be resources. Okay. Resources must be given to the child process somehow or the other. How? We'll have a look at now. Second thing is, in addition to these resources, every child process requires some initialization code. What is initialization code? Let me tell you. A process has been created to print, let us say some JPG file on screen. Okay. This process has been created. This is a new process. Now this specific process first of all need to be given with the name of the JPG file, the address of the JPG file, and the address of the console. Everything. These are the basic fundamental parameters that are actually required by every process when it is created. This is the basic data for any child process to execute. Got me? Right after which, every process requires, a job. when you create a child, of course, the child is created for a specific to execute a specific job. The job, what kind of a job can be given? We will have a look at. Okay. We will also see how the child executes. Within no time, I'm going to explain how the child, what are the execution sequence of the child. Right after parent creates a child, how the parent and child is going to execute. For that, we're going to take the example of Linux, after which you're going to get a complete clarity, complete transparency how the process creation is going to happen. Finally, after the execution, we need to terminate. The process need to terminate. Let us understand all these things. Okay. Now, first thing we'll talk about is resources. How the resources can be given. The resources can be given in two ways. The parent is responsible for giving away the resources. When I am created, I am given some resources. When I am going to create a child, some of my resources can be given to my child. And all my resources will be partitioned among all the childs that have been created by me. Let us say, being myself, I have created 5 children. For all 5 children, I am going to partition my resources. Okay, this is one way. Second way is, operating system is directly responsible for allocating the resources for any child process, but this is very dangerous. There is no practical limit on the number of resources for a child. Okay, the number of child that can be created by any parent. As there is no restriction, parent keep on creating as many childs as it want. I hope you got me. So every operating system follows the best practice, that is, parent is responsible for giving the resources to the child. Resources will always be given by the parent process to the child process. Next thing is initialization code. We already discussed about what is the job. The job is, when I create a child, two things that can be done. I can share my job. What I'm executing, a part of a job can be shared with my child. Otherwise, I can give my child a completely altogether a new job. Got my point? Any doubts? So if a parent process is executed, then child will also be executed. Now I am going to tell you, meanwhile, stay focused. Okay, you are going to get a complete detail. What is the sequence? Because we are entering into the concept of Linux, and I told you that the counter example that I'm using here, the case study that I'm using is here, Linux. To wait till the next slide, you're going to get the every clarity. Okay, how the resource sharing, parent child share the same resources. Okay, children share the subset of the parent resources. Parent and child share no resources. The third thing states that when a child has been created, operating system is responsible for allotting the resource. But this practice is not being followed by any operating system nowadays, because it will exhaust all the resources of the operating system. Okay, I hope you got my point. Next thing is execution. How the process will execute it. Parent and child will execute concurrently, and parent will wait until the child terminates. These are the two scenarios we can often see in different operating systems. How, what, when. Let us have a look at. Okay, here, stay with me. I'm going to give you a complete idea how this process creation to termination is going to happen. Okay, let us say there is a process P1. When a process P1 wants to create a child process within Linux, it is going to execute a system call which is called fork. A fork system call is going to be executed. To create a new child process. Stay focused. This fork has 3 outcomes. The fork can return a 0 value. The fork can return a 1 value. The fork can return a negative value. Okay. Sir, what is the difference? Simple. When the fork returns either 0 or 1, process child creation is successful. But when a fork returns a negative value, child creation is not successful. Child creation is a failure. Okay. Now, again, we know that as it's a negative value, it's just nothing but child creation is not successful. It's a failure. What is the difference in between 0, 1 and 1 again? Because when a fork returns 0, when fork returns 1, both leads to successful creation of a child process. But what is the difference? Stay focused. Let me take the help of the CPU here. Okay. Process X is executing. Process X forks. In tandem will result process Y to create. Right. Now, when 0 is the return value, then children creation is successful and children is executing now. X has been sent out from the CPU, Y, which is a child process, now executing. That is, when the fork returns 0, child has been created and child is executing within the CPU. Parent is in the main memory again. Okay, and fork returns 1. Child process has been created, but parent is still executing. I hope you got my point. Okay, did I make it myself clear? 0 means successful, child is executing within the CPU. 1 means child creation is successful, but still parent is executing within the CPU. Okay. Parent is waiting. Yes. Sir, if parent process is executed, then yeah, I hope you got it. These two are the parameters which states that successful creation of the child. Now, let us understand. Let us understand. For that, I will use, this illustrative slide. This is the main memory. This is the main memory. Okay. Here there is a CPU. Okay. Now, process X is forking. When process X is forking, let us say the child has been created. Fork returns 0. The child process, which is Y, is executed. Upon the creation, the child process, the very next step of a child process is it will execute a system call which is called EXEC. What is EXEC system call? This EXEC system call will allow this child process to use the parent address space, because this address space is resource of the the same resource which is going to be shared by both parent and child, right? Let us say this is the address space. 100 to 200 is the main memory space which is being used by the parent. Now, in order to use the same parent's address space, the child is going to execute one system called which is EXEC. EXEC will allow the child to use same address space as its parent. So as long as the child process is running, it will use only this address space as of its parent. Okay. Now let us say fork is returning 1. That means that only parent is executing, right? When parent is executing, most of the times the parent will execute one system call called wait system call. What is wait system call? The wait system call will suspend the parent process until and unless the child process gets completely executed. Because when I create a child, I will wait maximum most of the times that I will wait till my child gets executed and its job is finished. So this wait system call will be initiated, will be triggered by the parent process the moment the process creation is turned out to be successful. So this wait system call will make this parent process to be sent into the waiting state. I hope you got one more waiting state here. So far we have seen several waiting states. When a process is said to be in a waiting state, that is actually awaiting for a device, right? Now we have added one more waiting state of a process. This process will not be scheduled at all unless its child has been finished. When the child has been finished, again this process will be transformed from wait state to the ready state. I hope you got my point. I hope you got my point. Did I make it myself clear? Any doubts so far? Any doubts so far? Okay, fine. Next thing is, let us say, fine, process been created, child executed EXEC, so child is using parent's address space, after which parent has been scheduled. When the parent gets scheduled, parent called a wait system call, so that parent has been suspended till the child finishes. Everything has been finished. Now let us see, finally we have come to process termination. When the process gets terminated, the process gets terminated under normal circumstances, that is, the process is completely executed. When the process is completely executed, then it will get terminated within the required legitimate sequences. But sometimes what will happen is, when the process tries to use some unnecessary resources which are not allotted to it, the operating system would want to terminate it abnormally. Okay, but moreover, every process right after the creation, somehow or the other, it has to get terminated. For that, let us understand about a legitimate termination. Let us say this is Y process wants to terminate. That is, it is finished completely. Now it is going to execute a system call which is called exit. When exit system call is executed, this exit system call is going to make a request to the operating system. Mr. Operating System, I am done already. Please terminate me. So operating system will terminate this process and will relinquish all the resources, will get the resources which are being used by the current process, will be added to the resource pool of the operating system so that those resources can be allotted to some other processes. So this is the legal termination. Abnormal termination is there are several scenarios for a process to be abnormally terminated. It did not execute exit system call. Rather, it started using some other disk space. When it started using some other resources, operating system will kill that process. The other scenario is, let us say when parent is terminating. When the parent is terminating, most of the operating systems doesn't allow the child to be sustaining within the system. When the parent is completely terminating, when the parent is completely terminating, the child will have to be terminated by the operating system, which is called cascading terminator. Let us say I'm a parent, I'm terminating. I have created 100 processes which are active in the system. All those processes will be terminated along with me, which is called cascading termination. Okay, I think we do have a concept of Sati Sagamana earlier. Although, we should not entertain that, but it is still being entertained within the operating system. I hope you got my point clear, right? So this is all about a termination. But how? When a child process gets completely terminated, how the parent process would know that child process is terminated? Let us say I issued a wait system call. For how long I will be waiting? Till my child gets terminated, right? But how do I know? Understand carefully. When the child executes exit system call, it will send a return address. Okay, this return address will be passed as a parameter to the wait system call. Otherwise, the parameters, unless the exit system call is executed, the parameter space of the wait system call is null. Okay, it is awaiting the parameters to be received. The moment exit system call is executed by the child, the return address, return value, not return address, bigger pardon, I went by the flow. Return value, every function has a return value. Similarly, exit system call has also a return value. This return value will be passed as a parameter to the wait system call. So I will await till my wait system call receives the parameters. The moment the wait system call receives the parameters, then this process will be alive again, will be picked out from the waiting state and put into the ready state. Any doubts so far? Very good. Now let us go and have a quick look at of exit system call address space. I explained you process execute last statement. I completed completely. It is not abort system call. Abort system call is abort system call when parent wants to terminate child, it can use abort system call. But child when wants to terminate, it will use exit system call. Okay. Next thing is, yeah, inter-process communication, which is going to be covered in tomorrow's class. The process within a system may be independent or cooperating. But sometimes when a process want to communicate with the other process, it may request the operating system to communicate with the process. Cooperating process can affect or be affected by the other process. Let us say there is the compiler. Compiler is a program and loader is also a program. Unless the compiler gets executed, loader cannot be executed. These two must be executed in sequence and in tandem with each other. So these two are independent, cooperative processes. Now, and any such process will request the operating system to provide a communication among them. Reasons for cooperating is information sharing between because when the compiler gets executed, the output of the compiler should be used by the loader, as a consequence. Subsequently, computation speed up. Some processes when they execute together, computation will get speeded up. Modularity, we will have a better modularity in our program so that the CPU or the operating system will execute very conveniently at all. Okay, so two modes of the IP's inter-process communication is shared memory and message passing. Message passing is the simplest technique, but a shared memory is somewhat a complex technique. Shared memory design is very simple, but shared memory leads to a lot of troubles to the operating system, which has to be avoided by the operating system by using some excellent synchronization mechanisms such as semaphores. Okay, tomorrow we're going to discuss about that. Now let us go to solve the processes. Zombie process. Yeah, sure. Very good question. What is a zombie process? Are you with me? It's a very good question. That is, what is the zombie process? Okay. Listening? Yeah. Let us say child process. Okay. Child process executing. When the child process is executing, sooner or later, it is going to, exit. It is going to perform an exit system call. This exit system call is going to send a return value. Okay. This return value, where this is going to be transferred, these return values must be attributed as a parameters to wait system call. Okay. But hold on. When these return values can be sent as a parameters to the wait system call, these return values can be sent to the parameters to the wait system call only when wait is called by the parent. I will give you one wonderful scenario. There is a CPU. Okay. Stay focused. Some X process is forking. Right after the fork returns a zero value. That means Y has been created and X has been waiting in the main memory. Now, when X has been scheduled again, it is going to call a wait system call. But X hasn't been scheduled at all. Let us say for getting scheduled, there has to be several parameters. Let us say the priority of the X process is the least priority. X hasn't been scheduled at all. Meanwhile, Y is being scheduled. And finally, one last time when it gets into the CPU, Y found that, yeah, it finishes its execution. The job which is assigned and attributed to the Y has been finished. But till then, X hasn't been scheduled at all. When X gets scheduled, it may issue a wait system call, but it hasn't got scheduled. Now, Y has to, before the termination, it has to call exit system call. But exit system call is going to send the return values. But return values cannot be transferred to the wait system call, which hasn't been called yet by the parent process, right? Now, these return values are going to create a table. Operating system is going to create a table for these return values. Okay, hold on. What is this table, sir? This table is created a process which is left the system. Hold on, what we discussed. When a process left the system, none of the resources of that specific process must be active. Here, I do have an entity for a process which already left the system, which already is dead. Okay, now this entity, the table, is going to be a zombie process. Why it is called zombie process? This is a zombie process because it represents the values that are actually pertaining to a dead process. There is a reason why for a zombie, of course, this zombie becomes an orphan also. When, let us say, for one last time, let us say this parent process, this poor parent process has been scheduled finally. And then what it has to do? It has to issue a wait system call. When the wait system call has been issued, then the parameters has been collected from this table and can be sent. After this table can be deallocated. But unfortunately, the parent process decided to exit without calling wait system call at all. When the parent process enters into the CPU, rather than calling wait system call, it gets terminated by executing one more exit system call. Parent did not call wait at all and left the system. At that time, there is no way for this zombie table to be cleared. Okay, it will be left over in the operating system forever, which becomes an orphan. Okay, so operating system should be full of orphans, right? Actually, operating system doesn't allow this. In such scenario, operating system will attribute the responsibility of a zombie process or an orphan process to the root process. The responsibility will be given to the root process. Root process will periodically execute wait system call to get all the parameters from the orphan process, after which the orphans gets cleared. Why is wait system call is used? Let us say I created my child. As long as my child is executing, I don't want to execute. So that wait system call will be issued. Wait system call is going to make a request to the operating system that Mr. Operating System, as long as my child is executing, I don't want. I hope you got my point. To execute. Okay. Now I will start with the questions. The maximum number of processes that can be in the ready state for a computer system of n CPU is n square 2 power n independent of n. How many processes can be brought into the main memory? There is no, there is no calculation for this. Any number of processes can be coming in. N CPU, the number of the CPU has no effect on, rather, no impact on the number of processes that is coming in. In class, sir.
Anil sir, I'm looking at. Please keep the class on mute.
Yeah. Just a minute. Just a minute. Hold on for a while.
Audio, sir, not video. Please.
Yeah.
Solve questions and end the session, sir. It's already 1.5 hours.
Sure. I will do it right now.
Solve the question.
Yeah. Just a minute. Yeah. A process executes the code. When the for gets executed within a loop, the number of child processes that is created is 2 power n minus 1. This is very simple. This is 2 power n minus 1. Okay. So the total number of child processes that are created is 2 power n is, what is 2 power 3? 2 power 3 is equal to 8. That is total 7 processes will get created. So this is the rule. The number of processes that gets created is 2 power n minus 1 when the fork is getting executed within a loop. Okay. Yeah. Next thing is, consider the following code segment. If the fork equals to 0, there is something. Otherwise, something else. Let u be the values printed by the parent process and xy be the values printed by the child process. Which of the following is true? A, C, B, C, D. I told you one wonderful example for this. If the fork returns 0, then the statement which is executed is going to be executed by the child process. Otherwise, the scenario will become the parent process execution, right? So this will be the child process. This will be the parent process execution. So child is going to print a is equal to a plus 5. Parent is going to print a is equal to a minus 5. So the child is parent process plus 10, right? U, V, the values will be printed by the parent process. X, Y be the values printed by the child process. Which one of the following is true? Okay, so as you can clearly see, C is the option, because the difference between parent and child is parent process 10 plus 10 is equal to the child process. Okay, and hold on, parent and child process also printing the address of the variable, and you can clearly see both addresses will be same. As I told you for many times, both parent and child as they use the same memory space, the address that are going to be printed by both parent and child will be the same. V is equal to Y. Can I make myself clear? Any doubts so far? Okay. Next thing is, the process state transition diagram in below figure is representative of a batch operating system, an operating system with a preemptive scheduler, an operating system with a non-preemptive scheduler, a uniprogrammed operating system. Simple. Let us say new to ready, okay, ready to running, and running to ready, and of course from running to blocked as well as running to terminated. So which is this operating system actually? An operating system with a preemptive scheduler, okay, because when a process is moving from running state to the ready state, that means that the operating system using preemption. If there is no preemption, the legitimate states are from runnings to either waiting or terminated. Otherwise, when an operating system uses the preemptive scheduling, it goes from running to the ready state. Next thing is the time taken to switch between user and kernel modes of the execution be T1, while the time taken to switch between two processes be T2. Which of the following is true? T1 is greater than T2, T1 is equal to T2, T1 is less than T2. Understand something. Here, switch between the user mode to kernel mode within the process, and switch between the two processes. I hope you got it. Within the process, he's talking about mode switch in between user to kernel. Okay, and he's also talking about the total time to switch between one process to other process. Understand carefully. When a process is being switched with another process, mode switch is an integral part, because in order to switch the process from in order to switch from one process to another process, the operating system first of all should enter into the kernel mode. In kernel mode only, the operating system will switch in between the processes. Okay, so this process switch will also include the mode switch. So T1 is less than T2. The time taken for T1 is less than T2. T2 is the process switch, T1 is the mode switch. As the T2 also holds the mode switch, T2's time is greater than T1. Any doubts so far? Yeah. In the following process state transition diagram for a uniprocess system, assume that there are always processes in the ready state. Now consider the following statements. If a process makes a transition D, it would result in another process making transition A immediately. If a process P2 in a blocked state can make the transition E, while another process P1 is in the running state, the OS uses preemptive scheduling, the OS uses non-preemptive scheduling. Let us understand what is the first option. Makes a transition D. What is making transition D? Running to terminated. When a process is getting terminated, it would result another process making transition A immediately. What is A? Start to ready. Okay, so this is first scenario, and it is very evident from the discussion what we had, that when a process is leaving the system, that doesn't immediately get one more process into the main memory. It depends on from start to the ready. It is going to be dependent on long-term scheduler. Long-term scheduler will only come into the picture only when a few processes left the system. When a process left the system, immediately long-term scheduler doesn't come into the picture. Okay, so this is false. When a process leaves the system, that doesn't result one more process to be into the main memory at all immediately. Okay, so one is false. A process P2 in a blocked state can make transition E, while another process P1 is in the running state. Okay, what is P2? P2 can make a transition E. What is E? From the block to ready. Okay, so a process has been switched from the block to ready. While another process P1 is in the running state. Yes, one process is running state. Suppose some X process is running state. The running state of a process doesn't affect the transition of the other process from block to ready. So this is true. The OS uses preemptive scheduling. As you can clearly see, when there is a transition from running state to the ready state, the OS uses preemptive scheduling. So option 2 and 3 are correct. Here is C option is correct. The next thing is, consider three processes P1 and P2, P3 shown in the table. P1 is having arrival time is this thing, and the time units required this thing. The completion order of the three processes under the policies FCFS and round robin 2 is the CPU quantum of 2 time units are FCF, what are the options given? FCFS P1, P2, P3, RR2, P1, P2, P3. FCFS P1, P2, P2, P1, P3, P2. P1, P2, P3, P1, P3, P2. Anything that is making sense to you guys? Can I ask you? What is the correct option? What is the correct option here? See here, I will draw a Gantt chart here. Simply Let us follow this. This is a very simple question. Initially, which process is going to get into the system? The process is going to get into the system at the P1. Okay, P1 is going to get into the system. Round robin with the 2 time units. P1 is going to be printed at second millisecond. Okay, P1 is going to be printed. Now, observe main memory. In the main memory, we do have just P2. By the time P1 is being printed, we just have P2. Okay, there is no other process. Of course, there is P3 only is arriving at the 3rd millisecond. Okay, so P1 is going to occupy the first position in the ready queue, right? Okay, when P2 goes, P1 is occupying the first position in the ready queue. Okay, so after which P3 will come into the system at the 3rd millisecond. So the order of completion would be, in the round robin scenario, is P1, P3, P2, not P1, P2, P3. I hope you got my point. P1, P3, P2 is the execution sequence with a round robin with a time slice, time quantum. But FCFS, there is no doubt, the first process that goes in will completely execute and will come out. That is C. Okay. Next thing is, a scheduling algorithm's priority is proportional to the waiting time of a process. Every process starts with a 0 priority. The scheduler re-evaluates the process priority every t time units and decides the next process to schedule. Which one of the following is true if the process have no IO operations and all arrive at a time 0? Can you please answer this question? Can somebody answer this question? Can somebody please answer this question? This algorithm is equivalent to first come first serve or round robin or shortest job first. This is equal to round robin algorithm because for every t time units it is told. Of course, we can go into a lot of details here, but straight away, this statement make this entire scheduling algorithm as a round robin scheduling, because every t time units, after every t time units, when the operating system scheduler re-evaluates, of course t is stipulated and fixed, it becomes as round robin algorithm. Okay, how the round robin works? There will be a specific time quantum after which priorities will be evaluated, right? Yeah, making myself clear? No, just go through that 7th question again, just because obviously the option would be P1, P3, P2. It is not P3, P1, P2. The correct order is P1, P3, P2. Okay, so this is option B is correct option. Which scheduling policy is the most suitable for a time shared operating system? Time shared operating system meaning round robin. The time will be equally shared. The CPU time will also be shared equally. Okay, so round robin is best suitable for time sharing operating system. Here option B is correct. The next thing is, which of the following statements are true? Shortest remaining first scheduling may cause starvation. Shortest remaining scheduling, what is the first two options are the same? I don't know why it is. Of course, shortest remaining time scheduling may cause starvation, of course, because it is a priority schedule. When it comes to a priority scheduling, priority will always cause starvation, because as long as a higher prioritized process is getting executed, there is no way ever for a lower prioritized process to execute, unless the operating system implements to avoid this starvation by using some mechanism called aging. As the aging is not given here, of course, all the options are true. Round robin is also better than FCFS in terms of response time. Of course, when it comes to the response time, the best possible scheduling algorithm is a round robin. So, what is correct? Option 1, 2, and 3 according to the question are completely correct. Okay, that is it for the day. And yeah, tomorrow we do have the same session in which we are going to talk about synchronization. Here we have covered several questions, and also I gave you inside view of the operating system process creation, deletion, and all the other factors such as interrupts. Just access this class as many times as possible and share it with your friends so that you will have a clear idea and you can solve any question within this concept. Thank you so much. Anything else? That's it from my side, and see you same day, tomorrow at the same time. That's it for the day.